In grade 12 University Prep Physics. The unit is energy and momentum, though we don't touch on momentum to the last half. A lot of what the unit is just a review of what we did last year. We add another kind of energy called spring energy. But today we're just going to look at, or for this set of videos, we're just going to look at what we did last year. Okay? So we studied work and energy together because they're they're synonymous. It's like work is the transfer of energy, energy is the ability to do work. They kind of go back and forth. So sometimes they get used interchangeably, the terms. Work generally refers to motion, and so it's related mostly to kinetic energy. They have the same unit, which is joules. Work, just looking at work specifically then, the symbol, if you're using an equation, is W, and we get the equation is force applied times cos of whatever angle the force is applied at. If there's no angle given, then, thinking of a sine or a cosine curve for a moment, if the angle is 0, you should remember from math that the cosine of 0 is 1. So this would just be 1. Okay, so if there's no angle given, you can neglect it. Okay, and then delta D is displacement, how far something moves, and work is directly related to motion. Okay, the great thing about the first part of this unit, till we get to momentum anyway, is we deal only with scalars, meaning we don't really care about direction. We don't worry about positive, negative, as far as direction is concerned, and that sort of thing, north of east or whatever. This is just numbers. Okay. So just looking at a little example. Here we've got a golf club. We have a force of 42.3 and we have a distance of 2.52 meters. No angle mentioned, so you basically just assume it's 0. Like I say, cos of 0 is 1. So looking at the data given in the question, just sub in the equation. This is so easy. And then part B. So, check mark the question. Hard to check mark because I don't know what's a reasonable work, but we'll say that's a reasonable work. We don't really know. We just know it fits with the numbers, right? If knowing 40 times 2.5 is going to be about 100, right? In part B, it says describe energy transformations, because that's really anytime you have any motion or anything happens, it just means energy is changing from one type to another. And understanding that certainly helps you understand sort of all things related to oil production, energy production, all those things. So, I mean, this isn't related to that, but so what's the energy? Well, you have a golf club, it's got gravitational potential when you're sort of on the backswing. As you drop the club, not drop it, but swing the club, it gains kinetic energy and loses gravitational before the strike, right? When you hit the ball, the kinetic energy in the club, some of that turns into kinetic energy in the ball. And you lose a little bit of other energy too, to friction in the collision itself. And also you can hear it happen, right? So there's some energy lost to sound. So that's what I would say as the energy transformations. If you're given a question like that, just think about what happens and list as many transformations as you can. Example number 2 is lifting a turkey, which I guess is suitable because probably you're watching this at turkey time. From the floor to the kitchen counter, so that's the height. I guess the only things like really important to know about this, because this is easy, if you remember the formula that when you're lifting something, remember work is like the transfer of energy from one type to another. Well, really that's what it is. You're adding work and you're taking this turkey sitting on the ground and you're giving it, this is gravitational potential energy, which you may or may not remember from last year. So maybe the only thing in this question is making sure the 82.5 is listed not as centimeters, but as meters. Okay? And then you go through and do the calculation. It's pretty easy. And once again, is it a reasonable number? Well, again, what is 52 joules? We don't have a good feeling for what 52 joules are. However, I'm going to check mark it just because of the numbers in the question. 7 times 70, 7 times 10 is about 70, and then 80% of 70. Okay, number makes sense, right? It's within the scope of the numbers in the question. When it says to find the change in gravitational potential energy, this is what I was saying. We'll talk more about gravitational potential energy after, but from last year, you might remember that it's mass times mgh. It's gravitational potential energy. So when it was on the floor, the turkey had no gravitational potential energy relative to the floor, and then when you lifted it up, it had this amount. So the work you do then is really just you're adding work to the turkey, giving it gravitational potential energy. And so they're equal to each other. Okay, just another one. Power. Here's one. We don't do a lot with power in this course actually, but we did do it last year, and worth reminding ourselves what it is. So say we know a blender has 400 watts, and we want to know how much energy does it use in 1.5 minutes. Well, just some things that you may or may not remember from last year. Power is a rate of doing work, so it's really joules per second. A rate means it's something per time, right? We give it the symbol P, and it's work divided by time. Remembering that work, energy usage, work and energy are sort of synonymous. So if this is the information you're looking for energy, it's basically like you're solving for work. Okay? Something to notice in the data part, we have a power, the time has to be in seconds. So 1.5 minutes works out to 90 seconds to solve for work. And again, I don't know if that's a good number, but again, within the numbers in the question, without putting it in my calculator, I would know that that's 3,600, so we'll assume that makes sense. Okay, another one. Here we are, Fred and George, excuse me, are pushing a piano without wheels, so they're working against friction. How much work do they do? Given we know the force of friction, and we know how far it travels. So we're going to make an assumption. Oh yeah, constant speed, sorry. It tells us it's constant speed. So if you remember, if you do a free body diagram, if it's a constant speed, then the applied force must equal the friction force. The forward force equals the backward force. So that's why I can say that I can take that friction force, and it really is my applied force because it's constant speed. It'd be a different problem and involve more kinematics if not, and I wouldn't do that with the work unit. And we know the distance. We just want to find work again. No angle, so cos of theta is just 1, and pretty easily just 13,000 joules. And again, I don't know if that's a good number, but we do know that 5,000 makes sense that 5,000 times 2 is 10,000, so times 2.5 is about 13,000, so the number makes sense. Okay, another one of these, hopefully you find these easy. These are just applications of formulas, right? This time we have a lawnmower. Oh, we're given an angle of 30 degrees. And this is the force we're applying, that's FA, and there's our distance. So if you look at the givens, now we're going to use the full formula using cos of 30 as well. Okay, so you only have to worry about the angle. There's an angle given. No angle given, just it's cos of 0, which is 1. Okay. So those are just basic review questions. I think that's it for this. Yep, we'll talk about energy in the next video. Yep, that's it.